Hey, what's going on, Science 10s? What's going on? It's Mr. Walton here. We're talking about non-uniform motion. We're talking about acceleration today. Nice. Non-uniform motion occurs when an object's velocity is changing. That's right. We're talking about situations where an object isn't just going the same speed every single second, that kind of thing. So, in order to change an object's velocity, a force must act on it. Forces and acceleration are related to each other, and we're going to explore this a little bit later, but right now we're just going to really generally describe it. So, what we're going to do, I know this is kind of weird, but let's draw a ball sitting on a table. Sitting on a table, you got it, no problem. Mr. Walton's going to draw the best table he possibly can, and he's already off to a terrible start, but that's okay. Hey, how many legs does the table have? I don't know. Let's do this three-dimensionally. It's got a table coming back in the background there. Yeah, that's what I'm talking about. Oh, I feel bad for you. You got to watch this video. Okay, so we got a ball, and it's sitting on the table here. And let's think about this for a second. What will happen to you if you push the ball from its left side? Well, let's kind of define some things first of all. Usually the left is over here, usually, and we kind of define that to be a negative direction. Usually the right is over here, and we define that to be a positive direction. So what will happen to you, what will happen to it if you push the ball from its left side? So we're going to push it from its left side. So that means we're going to apply a force. We are going to apply a force from left to right. And what's going to happen to this ball if we apply a force here? Well, okay. Probably the ball was just sitting there originally, and if we push it from the left side, it's going to go to the right. So the ball will start moving in a positive direction. Now, I know that's not crazy to you. Like, you could probably ask a kindergarten kid or a grade 1 kid, and they'd be able to give you the exact same answer Mr. Walton just gave you. Does that mean Mr. Walton's as smart as a kindergartner? Probably not, but that's okay. So the ball will start moving in a positive direction. Okay, well, I mean, if it started at rest, right? Initially, what was its velocity? Velocity was 0. It was just sitting there. And then you pushed it, and then it started moving. So initially, its velocity was 0. Its VI was 0. And its VF was something other than 0. It was a positive, 3 meters a second. That's a crazy hard push, but you know what I'm talking about. So this is what we call acceleration. This is the acceleration that happens when an object is going no velocity and then it starts going a velocity. So did its velocity change? Yes. If its velocity changed, then it's undergoing acceleration. That's the big kind of moral of the story here. Okay, no problem. So, what will you have to do in order to stop the new motion of the ball? Well, the new motion of the ball, right? Let's kind of redo this here. So we've got our table. Our table sitting here. We got our table. And the ball, that's even worse than it was before. The ball's moving in this direction, right? It's got a velocity and it's moving in that direction. What are you going to have to do? What do you have to do in order to stop the new motion of the ball? If you want it to come to a rest, or if you want the motion to stop, you're going to have to apply a force in the opposite direction of the motion if you want it to stop, right? Okay, no problem. So a force must be applied in the negative direction. No problem. No problem. It's all good. So originally the thing is moving in a positive, so its VI is positive and its VF, well, if we stop this thing, its VF is going to be 0. So let's say it was going positive 3 meters per second and its final speed is going 0. Well, that's acceleration again. Its velocity is changing. That's what acceleration is. So now imagine the ball was already rolling in the negative direction. We'll just do this a little bit simpler. A ball is already rolling in a negative direction. What would happen if you applied a force to the ball directed in the negative direction? So if we take this and we apply a force to it in that negative direction, what do you think? Is it going to speed up or is it going to slow down? So it's already moving in the negative direction, and if we push it in the negative direction, yeah, it's going to speed up. So the velocity of the ball will increase. It looks like 2 words, but it's not supposed to be 2 words. I'm just really good at English. Okay, the velocity of the ball will increase in the negative direction. All of these are describing some form of acceleration. Acceleration is just when you start off with one velocity and you end up with another. So when the velocity of an object changes. Each of these situations is an example of non-uniform or accelerated motion. The ball either starts moving slowly and speeds up, or it's moving fast and then it slows down. Anytime an object changes its velocity or speed, we say that it's undergone accelerated motion. All right, that seems fair enough. So here, just by way of a few more examples, we've got a ball and it's already rolling, okay? It's already going in this direction. And if we wanted to increase its velocity in that direction, again in the positive direction, we must apply a force in that direction. So this is what we call positive acceleration. Because it's accelerating, it's increasing its velocity in the positive direction. So let's think about this. If the object was going, it was originally traveling in a positive direction. You can see that by kind of like the shadow that it's leaving behind. So it was originally traveling in a positive direction, but it's decreasing its velocity. So it's getting slower and slower and slower and slower and slower. What direction would you have to push this thing in order to have it go positive at first, but then slow down? Yeah, the force had to have been in this direction. So this is what we call negative acceleration, because it's accelerating in the negative direction. Here again, the object is traveling to the left in the negative direction. It's originally traveling this way, but it's decreasing its velocity. How could you decrease the velocity of something traveling in the negative direction? You would push it in the positive direction. So again, this is positive acceleration. It's all about what direction is the force being applied. It's accelerating in the positive direction. And then again here, it's going in the negative direction. It's originally traveling in the negative direction, but it's increasing its speed. It's going faster and faster and faster and faster and faster. So the force must have been that way. So this is another example of negative acceleration. That's just a couple examples for you. Well, there is a very specific formula that we use, and if you check on page 5 in your data booklet, the formula that we use for acceleration is A with an arrow above it is VF minus VI over delta T, and the V's have arrows above them as well. Remember that arrow just means it's a vector instead of being a scalar. So if you look at the units, acceleration is measured in meters per second squared, whereas velocities are measured in meters per second, and time is measured in seconds. And so this is important. We're going to talk a little bit more about this unit meters per second squared in a little bit, but let's go ahead and let's just kind of describe what's going on here in this formula. Acceleration is the change in velocity, and that's what we've got going on top, okay? Is basically acceleration is just the change in the velocity divided by the change in time. And the change in velocity is just the difference between them. We write them as the final velocity minus the initial velocity, and that shows the change in velocity divided by the change in time. So the best way to kind of talk about something is by really doing it. So acceleration defines how much the velocity is changing every single second. We're just gonna take a look at an example here, and then we're gonna go through some kind of reasons of what's going on here. Mr. Walton's dream car is the 2013 Toyota Sienna. Mwah, that's what I'm talking about. Oh, a beautiful vehicle. It takes 7.6 seconds for the Toyota Sienna to go from rest, or 0 meters per second, to a speed of 27.8 meters per second. That's basically 100 kilometers an hour. Or like loosely speaking, that's 60 miles an hour. So what is its rate of acceleration? Well, squiggly line. Let's go through here and let's try and define some things. It takes 7.6 seconds. Well, that sounds like a time to me, 7.6 seconds. For the Toyota Sienna to go from rest, if it's going from something to something, the start or the initial, right? The initial velocity is 0. So VI is 0 meters per second. And then VF looks like it's positive, right? Remember, this is a vector because it's got a direction on it. It's positive 27.8 meters per second. And it wants to know what is the rate of acceleration. Perfect, no problem. We can do this. Easy peasy lemon squeezy. Acceleration is VF minus VI over delta T. So remember, that's our first mark. Just writing down the appropriate formula that gets you 1 mark out of 3 usually, or like a half mark out of 2, something like that. So, do you know what VF is? Yeah, darn tootin', you sure do. It is positive 27.8 meters per second. And we're going to subtract the initial. Well, the initial, hopefully this makes sense, the initial was 0 meters per second. I don't need a positive or a negative on 0 because 0 is just 0. It's not really an integer. Okay, well, it is an integer. It's not really a whole number. Anyways, whatever. Acceleration is the change in velocity divided by the change in time, and it took 7.6 seconds in order to do this. So when I put this in my calculator, this is super important for you to pay attention to. I just pulled up my illegally downloaded calculator. And what we're going to do is we're going to go through here and we're going to put this into our calculator. We're just going to make sure that we understand what's going on here. Whenever I have 2 things being divided by 1 thing, I need to use brackets appropriately. I need you to understand that both of these things, the 27.8 and the 0, are being divided by 7.6. So we should probably do the top calculation first and then divide by 7.6, or put a big old set of brackets on the top. So this is how I would do this. I would say, okay, bracket 27.8 minus 0. No surprise that that's just going to be 27.8, and then divided by everything on the bottom. There's only one number on the bottom, so we don't need brackets. 7.6. Perfect. And that's going to give us 3.657894. Okay, perfect, no problem. 3.657894, blah, 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 blah. Well, what do we get? What are our units going to be? is going to be meters per second divided by seconds again. We're dividing by seconds again. Nothing's going to cancel out here. We're going to get meters per second squared. This is going to be positive. Well, what's this answer to the appropriate number of significant digits? Well, we had 2 significant digits here, right? The 7.6, that's 2 significant digits. Here, 0, if you're starting at rest, that's a defined number. So that's infinite significant digits. And here, that's 3 significant digits. So when you're multiplying and dividing, you got to take the lowest number of significant digits. So we got to round to 2 digits. The 3.6 is actually going to turn into 3.7, positive 3.7 meters per second squared. Perfect. That's what the rate of acceleration is in my dream car, the 2013 Toyota Sienna. So let's think about what that actually means. What this means is that every second, my car is increasing its speed. When I say positive 3.7 meters per second squared, that means that we are increasing our speed. We're increasing our speed or velocity by 3.7 meters per second every second. I could have written this as 3.7 meters per second per second. That's kind of the way you want to think about it. Or per second, kind of like that. Ugh. There we go. I know that doesn't help some people, and that's totally fine. So we're going to take a look at a little bit more of a kind of a different calculation here. So in contrast, the Tesla Model S has a much better rate of acceleration than the Toyota Sienna. Not a surprise. It's an electric vehicle. Electric vehicles almost always have better accelerations. So the Model S can accelerate at close to Mr. Walton, positive 9 meters per second squared. Let's think a little bit deeper about what that means. What we're going to do is we're going to kind of map out what this car is doing at a bunch of different times. So at 0 seconds, at 1 second, at 2 seconds, at 3 seconds, at 4 seconds, at 5 seconds, blah, 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 blah. So if we have a rate of acceleration of 9 meters, positive 9 meters per second every second, what that means is every single second, we're gaining 9 meters per second. Our speed is increasing by 9 meters per second. So at a time of 0, we're going 0 meters per second. Hopefully that makes sense. We're starting at rest. Now, after 1 second, if we accelerate after 1 second, what will our speed be after 1 second? Well, if we increase 9 meters per second every second, we'll be going 9 meters per second. Now, 1 second later, we'll have added another 9 meters per second. So we'll be going 18 meters per second. Another second later, we're going to be going another 9. So add another 9 onto this. We're going to be going 27 meters per second. And then we're going to be going 36. And then we're going to be going 45 meters per second. And so this, in general, this is kind of what acceleration means. It means how much are we gaining or losing off of our velocity every single second. Now, you could do something a little bit even more interesting with this. You could say, okay, how much time is it going to take me to get to, 63 meters per second? So what we could do is we could kind of carry on this trend a little bit. We could say, okay, well, 6, 7, 8, 9, blah, 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 however many seconds. So another second later, I'm going to be going 54 meters per second. Another second later, I'm going to be going 63 meters per second. And so after 7 seconds, we will have gone 63 meters per second. That's what our final speed will be. So you need to know what the initial velocity was in order to figure out what the final velocity was. And hopefully that makes a little bit of sense. So just a couple more examples. Mr. Walton is driving down the highway at a velocity of positive 32 meters per second. He sees a deer run onto the highway and slams on the brakes. I hope I spelled brakes right. Goodness gracious. If it takes 4 seconds to come to a complete stop, come to rest, what is the rate of acceleration of the vehicle? Squiggly line. So let's think about this. Let's go through and try and kind of define some things. Mr. Walton is driving down the highway at a velocity of 32 meters per second, positive 32 meters per second. That sounds like VI to me, my initial velocity. He sees a deer run onto the highway and slams on his brakes. It takes, that's a delta T, 4 seconds to come to a complete stop. That sounds like my VF. What is the rate of acceleration? So let's do this. VI is positive 32 meters per second. VF, we already know, is 0 meters per second. And it takes 4 seconds to do that. What is the rate of acceleration? So we use our trusty formula. The rate of acceleration is VF minus VI over delta T. So if my final velocity was 0 meters per second, and I'm going to subtract my initial was positive 32 meters per second. And it took 4 seconds in order to do that. So again, let's break out our calculator. Turn it on. And let's do this. So brackets, because we've got 2 numbers on top divided by 1 number on the bottom. So 2 numbers on top, we need brackets. 0 minus positive 32, so minus 32. Divided by 1 number on the bottom, we don't need brackets, 4. You could put 4.0, but it doesn't really matter. Good, so that equals negative 8. So I got 2 significant digits on top, 2 significant digits on the bottom, so I need to round to 2 significant digits. Meters per second squared, because that's what the units are for acceleration. Okay, no problem. So let's see if this makes sense. I've got a car. Mr. Walton's driving down the highway. Okay, so I've got a car. That's Mr. Walton's car. I know it's terrible. Just deal with it. Okay, he's going that way in a positive direction, and then he slams on the brakes, and he starts to slow down. So it sounds to me like there's a force acting that way. Does it make sense that the acceleration would be negative if the force is in the negative direction? It sure does to me, okay? What does that mean? It's a rate of negative 8 meters per second squared. Well, let's think about this just a little bit more in depth. You don't have to do this every time, but let's talk about our time in seconds and then our velocity in meters per second. So at 0 seconds, we were going positive 32 meters per second. After 1 second, what happened? We were going 32 meters per second, but after 1 second, we will lose 8 meters per second. So we will have gone, our new velocity would be positive 24 meters per second. After 2 seconds, we're going to lose another 8 meters per second. So that means we're going to be going positive 16 meters per second. After 3 seconds, we're going to be going positive 8 because we lose another 8. And after 4 seconds, we're going to be going 0. Hopefully that makes sense. It took us 4 seconds to come to a complete stop. That's just kind of an explanation. Maybe that's helping you, maybe it's not. Last problem, last example. An object is falling at a rate of negative 5 meters per second. And the reason why it's negative is because, if something's falling, right, Well, this is a positive direction and this is a negative direction. So it's something's falling, it's going a negative direction. Okay, squiggly line. As it falls, it starts to accelerate due to the force of gravity pulling it down. If it takes 7.4 seconds to reach a final velocity of negative 78 meters per second, what was the rate of acceleration due to gravity? Well, let's do this. Let's summarize our stuff. An object is falling at a rate of negative 5 meters per second. That sounds like an initial velocity to me. It starts to accelerate, okay. If it takes 7.4 seconds to reach a final velocity of negative 78 meters per second, what is its rate of acceleration? Vf minus Vi over delta t. So let's plug in our information because we don't have to do any rearranging for now. So Vf was negative 78 meters per second. And we're subtracting our initial, which is negative 5.0 meters per second. And we're dividing by delta t. Delta t is 7.4 seconds. Let's take out a calculator. So we got negative. So I'm going to put brackets, right? Two numbers on top. So negative 78. And then minus a negative. When you minus a negative, it's like adding a positive, right? But let's let the calculator do all the heavy lifting, okay? So minus negative 5.0 bracket, okay? We could let the calculator do all the dirty work for us. Divided by 7.4. So equals negative 9.86486. Negative 9.86486, blah, 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 meters per second squared. When I look at this, we got to round two digits. So we got to round to two digits. So negative 9 point, is the 8 going to stay at an 8? Nah, it's gonna be 9 meters per second squared. Perfect. Hopefully that makes sense. An object's falling down, and it's going faster and faster and faster down. Which way is gravity pulling or pushing? It's pulling down, right? So that's why acceleration due to gravity is negative, because it's being pulled in a negative direction. So hopefully that makes sense. Anyways, I got a couple problems that I want you to do. We're over on the next page now, so we got a couple problems, two numeric problems and kind of one, just like a conceptual problem. So try them out and look at the filled in notes if you want the answers for these questions. Again, let me know if you have any questions. Come see me in the office hours, 10:45 to 11:15 every single morning. I haven't seen anybody in a really long time, which is pretty sad. I'm starting to get lonely. So if you got any questions, let me know. Hit me up. Okay, see you later.